So this is the part of our studies where we get to kind of venture back into history and take a look at what wood looks like as a structure's component or material if we're going to use. Now, wood was the first material that ever was used to build an airplane, and the reason being is that it was readily available. Everybody knew how to work with it, and that's how everything was made. Literally everything at that point in time was made out of wood. And so naturally, whenever the Wright brothers sat back and said, like, hey, look, we're going to build an airplane, they started with the wood frame. They put cotton fabric over it, doped it so that way it would be retardant against water and other various contaminants. And then they put it, the first engine onto it, and you get powered flight. From there, that was their starting point. So naturally, whenever they did version 2, it was more wood, and then version 3, and so on and so forth. So real quick, we're going to kind of go over kind of like the milestone aircraft of wood, and then up to the point where you get to the de Havilland Mosquito, and it became very apparent that they needed a different type of material. And at that point, the Industrial Revolution had really changed the way that everybody built things. Now, the next major aircraft that comes online after the Wright brothers that really is kind of like the state of the art is the Sopwith Camel in World War I. Now, World War I really blew up the aircraft world, but after it was over with, it came to a standstill, and wood aircraft didn't really see just a whole lot of innovation. But then whenever World War II comes around, people had been thinking about like what the next aircraft needs to look like. How could they improve performance? They had learned a lot from World War I and in the interwar years through civil aviation. And so the next aircraft that really comes about that is made of strictly of wood, that really is kind of like state of the art, is the de Havilland Mosquito. And here you can see the de Havilland Mosquito landing on doing some of the first aircraft carrier landings that are out there. So things that we take for granted now, like tail hooks and catapults, these were all being developed at the time. Now, the problem with wood is that like it has a limited amount of strength, and it is susceptible to rot and all kinds of other damage. So once some of these new stressors get applied to the aircraft, all of a sudden you start seeing them break apart and crash and having all kinds of issues and problems that before they never really had. And so they needed to come up with some new way to be able to employ the aircraft so that way they could continue to outperform the enemy. Okay, so inspection of wood structures. The first thing, the aircraft has to be dry. It needs to be, you have to open up all the access covers and panels just like you would with a normal metal airplane. But what you're really looking for here is glue deterioration and any evidence of moisture and or decay or deterioration of any sort. You're basically making sure that the aircraft isn't breaking down because of the stress that's been put in. So you begin the examination with the external aircraft, and you can't accept any sort of departure from any sort of original contour or shape. If it was built to be a certain way, then it needs to be that way. Any other difference is pointing towards a breakdown of the internal substructure of the airplane. Okay, where light structures using single plywood coverings are concerned, some slight sectional undulation or bulging between panels may be permissible if the wood and glue are sound. So over time, because it's a natural organic substance, it's going to change a little bit. It's going to warp and want to move. Now, if there's a little bit of that, that's okay, so long as it's still structurally sound. But if it's anything beyond that, it needs to get replaced. The contours of alignment of the leading and trailing edges, however, are of particular importance. A careful check should be made for any deviation for the original shape. So it means the leading and trailing edge have to stay exactly where they were at during construction. If they change just a little bit, the airplane won't fly right, and then you'll end up having a problem. Okay, splits in the fabric covering the plywood surface must be investigated to ascertain whether the plywood skin beneath is serviceable. Okay, keep in mind, we're really concerned with like wood rot here. It's like one of the chief things you're looking for on an airplane is any sort of decay or rot or breaking down of the substructure. A musty or moldy odor apparent as you remove access panels during the initial inspection is a good indication of moisture, fungal growth, or possible decay. And so anytime you smell something weird, something looks weird, one of the questions they'll ask you on your A&P exam and on your eyes. Like, what do you do with wood rot? Or how do you detect it? So you detect it by just probing it with something, with a sharp metal object. You take a scratch awl, stick it in there. If it sinks and it's not hard, then you know that you have some wood rot. And then what do you do with it? The answer is really simple. You replace it. You just simply take whatever that piece is out, even if it's the main spar on a wing, it comes out and the new spar goes on. Um, yeah, so let's talk about glued joint inspections. Okay, this is where we really start to see the difficulty in wood airplanes. Now, if you look at the graphic here, you see there's an inspection hole, and then as you come through, anywhere that's indicated by the letter A, so all those parts in that laminate right there, that's where glue's at. And any sort of glue deterioration is an indication that that airplane is not flight worthy anymore. So the inspection of glued joints in wooden aircraft structures presents considerable difficulties. It's difficult to positively assess the integrity of the joint. So even if you think that the glue may be breaking down, there's not a good way to do a non-destructive test to ascertain whether or not it's good or bad. Because what you don't want to do is go into a good structure and mess it up, trying to determine whether or not it's a good structure or not. So whereas we can use like ultrasound on composites, we can use eddy currents on aluminum, and all kinds of other methods. But we can't. There's just nothing that really fits the bill like that with wood and glue. So what causes the glue to break down? Three things: chemical reactions of the glue caused by aging and moisture, extreme temperatures, or combination of those factors. Mechanical forces is the second one, caused by wood shrinkage. So over time, moisture will leave the wood and it'll start to draw up, and as it draws up, it pulls on that glue and the glue gives away. And then lastly is development of fungus. Fungus will really break down glue. So to perform a more detailed inspection on a wooden aircraft structure immediately beneath the upper surfaces for signs of deterioration of adhesives has to be looked for. So like right below where the surface is at, because the surface of the skin gets hot because of sun, especially if the aircraft is painted black, that will cause the glue to break down. Then aircraft exposed to large cyclic changes in temperature. So if you think like Alaska, you think like Talkeetna, they can get up to like 100 degrees sometimes, but then in the wintertime it'll be super duper cold because of the latitude that place is at. It's going to just absolutely wreck wood airplanes because of those cyclical changes. Now, if you go down to the equator, maybe on some desert somewhere where there's not a lot of moisture, that's like a good, happy place for wood airplanes. Not a whole lot of like crazy changes. There's gonna be some because it's desert and day and night, that kind of thing. But any sort of like nice, stable temperature with the low humidity, that's a wooden aircraft land. Anywhere else, it's just gonna absolutely wreck them. So over a period of time, however, differential loads are transmitted across the glue joint because two members do not react identically. Glue tends to deteriorate with age as well. So over time is like the enemy of all aircraft, but especially wood aircraft, because as the aircraft flies, those different, like just coming from different trees, and those different, just like different people grow up differently and have different strengths and weaknesses. Trees are the same way. So you will end up having different. Wood react differently in like a laminate layup structure, like you're looking at here on this graphic. One wood may handle the load really, really well, and the next one won't, and that difference in handling that load will cause slight deviations in the way that they handle any sort of flight load that gets put on them, and that causes the glue to become strained. And then just over time, glue breaks down anyway. So as time goes on, that glue really starts to take a beating. And so a wood airplane has a life limit on it from both the wood and from the glue perspective. So if we're going to inspect glue, you're going to use a magnifying glass where the glue line tends to part or where the presence of glue cannot be detected or is suspect. Probe the glue line with a thin feeler gauge. If any penetration is observed, any at all, the joint is defective and the structure dictates the feeler gauge thickness. But use the thinnest feeler gauge whenever possible, so that way you can detect the failure as early on as you possibly can. So that's basically what you're going to do with glue. Like you're always looking to see, is the glue failing or is it not? Okay, so there's two main things that you're really looking for whenever you're inspecting the wood. First off, and probably chiefly, is decay. So wood decay and dry rot's not necessarily that easy to detect. But what you're looking for is dark discolorations in the wood or gray stains running along the grain. They're indicative of water penetration. Anywhere that there's water, there's probably going to be damage, and that's what we're looking to try to find. Another method of detecting water penetration is to remove the bolt holes and holding the fittings together to spar root end joints, aileron hinge brackets, etc. So just take out the hardware and then look and see what's behind it. A lot of times, if there's water in the airframe, they'll basically either get trapped there or they'll sweat out right there, or whatever, and that'll help you to detect it. Control system openings, fastener holes, cracks, or breaks in the finish, in the interfaces of metal fittings, the wood structure, or points that require additional attention during inspection. Additionally, any windshield or window frames, the area under the bottom of the entrance of cargo doors, the lower section of the wing, the fuselage, are locations that require detailed inspections for water damage and corrosions on all aircraft, but especially on wood ones. All those places are places where the aircraft goes from being like a nice, uniform surface to some sort of transition, and that's where water will generally pool at, especially on the bottom. That's kind of what you want to look at. You also want to examine the structure for other defects like mechanical failure. Mechanical failure, basically meaning that like any load carrying member that has bruises or crushing or any kind of crack, that especially with wood. Now, with aluminum and even composites, they're really resilient to that kind of thing. So, provided that the engineering was done correctly, it takes a pretty wild pilot to crack aluminum or crush or whatever else. However, with wood, because it ages so rapidly, you can get those types of failures, and you end up having to change them out. So once again, you check all metal fittings that are attached to wood structures for looseness, corrosion, and cracks or bending. A lot of times, if the substructure has been somehow damaged through compression or something or another, the hardware will start to be able to move, and if you detect any kind of looseness, that is going to spur on further investigation. Like, why was it loose? Was it just not torqued correctly? Has it come loose? That's where your witness marks will really come into play. Make sure that whenever you install anything in a wood aircraft, you have those witness marks to help track any sort of movement of the hardware. Inspect structural members for compression failure, which is indicated by a rupture across the wood fibers, and we'll put a graphic up that kind of indicates that. Those compression failures, as they cut across the fibers, that's a key indicator that there's something failing on that airframe, and then it's not flight worthy, and that has to get replaced. And I'll tell you, that's the one test question on the IA about wood, is about compression failure and how to detect the cracks. So essentially, what you're looking for, you're looking for glue deterioration and wood deterioration. That's the two main things you're looking for on a wood airframe. You're looking for decays, cracks, and any sort of like water accumulation anywhere on the plane. Because where there's water, you're eventually going to get rot. There's a bunch of different ways that you can go about employing or tools and techniques you can employ to inspect a wood aircraft, to include tapping the area with a light plastic hammer or a screwdriver, like the back end of a screwdriver. It works really well. This should produce a sharp, solid sound, but you'd have to kind of really hear it to know what right sounds like. So really, it's kind of like tapping on a wall looking for a stud, except for in this case it's reversed. The studs are everywhere, and you don't want any hollow areas. If you hear a dull sound, then that's where you need to start probing and try to figure out what's going on there. Using a scratch awl or a thin bladed screwdriver, help probe the area, will help determine whether or not there's any dry rot or decay. And the wood structure should always be firm. Anything that's soft and mushy needs to get replaced. But that's kind of the basics of wood aircraft inspection. And it's not really like it's nothing that's super difficult. I mean, if you've ever like just inspected wood in general for anything, be it a boat dock or whatever, you know what rot looks like. And so you don't want any rot, any cracks, any glue determination whatsoever, because this is in this era of aviation, whenever this was the kind of like the status quo, planes regularly broke up in flight. They just fly along, nothing really happening. Then one of these failures happens, and the whole plane just falls apart in midair. You don't want that. So like have a high degree or a high standard that you're inspecting any wood aircraft to, and hold it to it no matter what, because literally like a little bitty crack somewhere could be the last like the one and only red flag to a catastrophic failure of that airframe. Okay, this is a graphic that basically shows what the relation between the wood shrinkage is to moisture content in relation to a brand new lumber that's coming off the yard. Now, the reason I bring that up is for two reasons. One is that the wood that you're getting needs to be PMA certified to do any kind of repair or replacement or even building an aircraft because of charts like this. Like it needs to we have to know for sure, because this is people's lives we're talking about, that all the moisture that was in the wood has been pulled out, and that no new moisture is introduced into it. The second reason I wanted to point it up is I wanted you to see the bell curve effect that's happening here. Now, obviously, having low levels of moisture will help, like on the far right hand side, helps curtail any moisture or any warping or any shrinkage that ends up happening. But having a lot also doesn't necessarily make it shrink at all either. All right, so like what we see happen here is that middle of the row, that 32 to 22%, is really where moisture or where wood shrinkage kind of peaks. Now that's dangerous because that wood is going to look like it's dry, but it's actually not. There's moisture in it. So let's say you go and fly through the rain, you think like get the airplane all dried out, and you think it's good. Well, that wood is basically a sponge that's pulled that moisture into it. And to have the maximum amount of shrinkage, it only really needs about 30% of the wood to be wet. Now, as the wood shrinks, you're also going to have warping. You're going to have it pulling away from the hardware, and you're going to create space for more water to get into. And it can very quickly become a self-licking ice cream cone. And that's why moisture is so incredibly toxic to wood airplanes. Now, that also opens up the door to fungus. As you think a hangar where they put it in there and they basically close the lights, you have a enclosed space with water with no light penetration. It's the perfect place for fungus to start to grow, and then that sort of fungal rot very quickly will destroy fabric that covers that wood well before it destroys the wood itself. And so that's also another effect or another problem that you're going to need to look into. That anywhere that you can introduce water, you're going to get fungal growth as well, especially on fabric. But so this graphic kind of highlights how little moisture it takes, and then how the most like heinous effects of moisture on the wood may very well be undetectable to you. So you need to have a super high degree of or a super high standard to whenever you're inspecting a wood aircraft. Okay, so we're going to go over what are the characteristics of wood that gets used on aircraft. Now, there's a bunch of different types, and we're going to talk about those different types, like those species of wood that could potentially be used. But ultimately, it all boils down to these four principles of wood that's being used on aircraft. First off, solid wood, or the objective solid, is used with nouns such as beam. Spar refers to a member consisting of one piece of wood. So it means that a spar, a beam, a longeron, or whatever, all comes from the same tree. It's not spliced, it's not jointed, or anything else like there. The reason being is that the wood is the strongest whenever it's in that state. Any other type of compilation that you could come up with is going to be weaker than that. Secondly, laminated wood is an assembly of two or more layers of wood that have been glued together with the grain of all the layers or laminations approximately parallel. Now, this is kind of like the basic idea of like a Mongol bows, that was the first kind of composite materials that they took different types of wood and layered them at different points in the bow to create different effects, so that when they started optimizing it from shooting an arrow from horseback, and that was the first composite structure. And you're going to see this same principle of lamination that's going to come into it whenever we talk about composites here in a little bit. That essentially all laminated wood is that there's a thin layer at the bottom, then then it's glued another layer that's also thin. It's glued this on top of it. Most of the time, with grains being perpendicular to each other. But if they needed a bow or something, if they needed some sort of effect, then maybe they put the grains in line with one another, or maybe at a slight angle. Just depending on what you're trying to accomplish. But that lamination is something that you need to get really familiar with, because that technique persists beyond wood and goes into composites, and in composites that is a big deal. But it starts here with wood. All right. Plywood is an assembled product of wood and glue that's usually made of an odd number of thin piles or veneers, with each grain layers placed 9 degrees with the adjacent ply or pile. So another type of lamination. But that is the definition of what plywood is per the FAA. And then lastly, high density material including compreg, impreg, or similar commercially made products, heat stabilized wood, or any hardwood plywoods commonly used as a bearing or reinforcement plates. So that's like another a variation of wood that you could end up using, where they've taken all these different little parts and pieces and then pressed them together to use them as plates. So anyways, so that's the very kind of broad overview types or characteristics of wood that we're going to use on an airplane, be it for construction or. Okay, so this is figure 6-10 in the 8083, and it's going to talk about all the different types of wood that could potentially be used on an airplane. Now, I will tell you that spruce is definitely the preferred choice and the standard by which everything else gets measured. Now, if you look at this graphic, which may be difficult for you to read if you're depending on what you're watching this on, but you can see it in the 8083, which is free online. It's linked in the description on Figure 6-10. Anyways, spruce has strength properties that becomes 100%. That says like, hey, look, this is the bare minimum. Is that wood that we're going to use has to exceed spruce. That's going to be like the acceptable standard. And then the maximum permissible grain deviation, meaning how much how knotty it is, basically how it goes all over, is 1.15. All right, and then everything else basically is going to hold to that standard. So what you won't see is things like a boat arc or plum or a fig tree or whatever, because they're too knotty and they turn around and have all kinds of deviations into them. That number would be much higher. But spruce generally grows really straight. Douglas fir, the second one on there. If you've ever been out to the Pacific Northwest, those firs are like super duper tall, and they grow straight as an arrow. So very good, wood. And it's no doubt that the reason why Boeing got its start in Seattle, and even really up and down the West Coast. I mean, Lockheed Martin's in Palmdale, or that's where they got their start at. And that when you start thinking about the access to really high quality wood feeding into aircraft production, well, that makes sense, because that Doug fir, noble firs, spruce all grows in that area. And there's noticed that every single one of them has their own little nuances that can be used anywhere on an airplane. Now, some of those are really good. Like if you look at spruce, the comment is excellent for all uses, considered standard for this table. So that's like if you're using spruce, you're good. But if you go down to like northern white pine, it makes a point to say that it has excellent shock, or is low in hardness and shock resistance. So you need to think about that whenever you're replacing, like if it's a part of landing gear, you don't want to use white pine on there, because the first time you have a hard landing, it might blow it apart, and then next thing you know, the airplane's wrecked. And so there's little nuances like that you want to take into consideration. All solid wood and plywood used for construction and repair of aircraft should be of the highest quality and grade. Matter of fact, there's a mil spec for it. The mil spec for solid spruce is mil S-6073, and for plywood it's mil-P-6070B. Now, trying to find a supplier that can get that to you might be somewhat difficult, and you would want them to any part that you get that's been milled have a PMA approval if you can find it. But a lot of this stuff is getting more and more difficult to find. It kind of went through this is wood was like kind of the staple. Then it became kind of like the old man's airplane, and then it became kind of the boutique kind of cool guy airplane. Now it's like super duper rare, and there are still wood airplanes that are out there flying around, and there are supply chains that service those wood airplanes. So like Stearman's, like really big in the Northwest. You'll see like these old guys that fly Stearman's around, and there's a lot of those Stearman's are still made of wood, and so there are guys that work on them, but it's a very niche side of aviation. Okay, so let's talk about some defects in wood that we can have. Now, just like anything else is natural, nothing is going to grow perfectly, perfect and uniform. There's all going to have their own kind of personalities. So with those personalities come defects. Now, some defects, just like with some people, we can accept them, and then some defects we can't. And so it's not really that different. So the first one we're going to talk about is cross grain. So cross grain or spiral grain, diagonal grain, or combination of the two is acceptable if the grain does not diverge from the longitudinal axis of the material more than specified in the chart that we just looked at, so 1.15. A check of all four faces of the board is necessary to determine the amount of divergence, and the direction of free-flowing ink frequently assists in determining grain direction. That's basically saying that so long as the grain doesn't diverge too much and doesn't get super wonky, then we can still use that board. So that's the first defect, is cross grain. The second one that we want to look at is hard knots. Hard knots or sound hard knots are up to 3 1/8 inch in diameter are acceptable if, and there's a couple of like caveats there, if they're not projecting portions of the I-beams along the edges of rectangular or beveled unrouted beams or along the edges of flanges of box beams. Basically, as long as they don't have anything that sticks out that causes a problem. Number 2, they do not cause grain divergence at the edges of the board or in the flanges of a beam more than specified in the previous chart that we just looked at. And they're in the center of the third beam, not closer than 20 inches to another knot or other defect. So they can only happen at so much frequency. So if it's all knotted up and there's too much, it means that the board's not really that strong, so we can't use it. So cross grain, knots. We talked a little bit about the diagonal grain. Let's look at another graphic. Okay, pin knots are another one, whereas a knot is a full-grown limb that has come out of the tree, and then we sawed a board out of the trunk of the tree, and then you get the knot that's left over, and it can be formed by like other kind of little clusters that grow on the side of the tree, or maybe it changed directions. That's how you get knots. Pin knots, on the other hand, are the little limbs that stick off. You've seen them before. If you've seen like an old oak tree, they'll have these little bitty small limbs that will grow off of them. Whenever you form a board, it makes these little knots. Now, granted, these pin knots and small clusters are acceptable if they produce only a small effect on the grain direction. Basically, as long as they're small, no one really cares about pin knot. This slide, don't let the 10 millimeter throw you off. It's not aviation grade information. It's just there to show you the what a pin knot looks like. But so long as they're sufficiently small, we don't have a problem with them. Okay, pitch pockets, they're these little voids in the wood where pitch from the sap has accumulated. They're acceptable in the center portion of the beam if they're at least 14 inches apart when they lie in the same ring growth and do not exceed 1.5 inches in length by 1/8 inch by 1/8 inch deep. And if they are not along the projecting portions of I-beams, along the edges of rectangular or beveled or routed beams, or along the edges of flanges of box beams. So basically, you can have pitch pockets so long as they aren't too big, they aren't too frequent, and they're not at any critical load carrying area. Reason being is that that's technically a void in the wood. Now it's filled with pitch, but pitch is going to deteriorate just like anything else. So eventually a gap will form there. Now if the structure isn't super strong or super load induced, or like it's not going to carry a lot, then we don't really care about it as much. However, if you put it into a strut, a spar, or something that's going to carry a lot of weight, that is going to be the future home of a crack and eventually a failure. So we don't want pitch pockets in those areas. Okay, next one is going to be mineral streaks. They're acceptable so long as they don't reveal any decay. It's largely just cosmetic. They're not necessarily anything saying that the wood is faulty in that area, so we can affect those defects. Some people even prefer these because it gives the wood grain a little bit more color, a little bit more character. But on the airplane, We don't really care because it doesn't have a direct structural implication. Let's talk about what is not acceptable. So back to this slide. On the top left-hand corner, we have a shake. Now, what's a shake? Shakes are longitudinal cracks, usually between two annual rings. It means that it's already cracked and it's going across two rings. There's other kinds of ways that this could manifest. We call them splits and checks. Splits are longitudinal cracks caused by artificially induced stress. It means that like you've bent the wood to cause a crack, whereas a shake is a longitudinal crack that's naturally occurring. Just the wood's starting to pull away from itself for other reasons. A check or longitudinal cracks extending in general across annual rings. So that means that like anywhere that the wood has cracked diagonally across the ring. So if you think like old stumps will a lot of times have checks in them. You go and look, and they're starting to deteriorate, and they'll start to crack from the center out. Especially old pine stumps. Yeah, checks, shakes, and splits, can't have those. Okay, compression is another one. Now, I don't mean compression as in like load induced compression, but compression in terms of the way that the tree grew. So, what is compression? It's very detrimental to the strength and is difficult to recognize readily, but compression wood is characterized by high specific gravity, has the appearance of an excessive growth of the summer wood. So notice the gap in the rings and the real dark color means that it grew really fast one summer, likely because there was a lot of rain or whatnot. In most species, it shows a little contrast in color between spring wood and summer wood, but if in doubt, reject the material or subject samples to a toughness test to establish the quality of the wood. So you can put it into a toughness tester and see if it passes this old sniff test. But in all reality, like the easiest thing to do is just not even mess with any of that. Just get some quality wood because usually it's in readily available supplies. But yeah, so compression. So those are compression rings that you'll see on wood. Just stay away from them altogether. Yeah. Now, there's the other type of compression of where it's been artificially induced and caused the wood to start to split across the grain, is like you can see here. This is just pieces of wood somebody put into a machine that basically causes those types of failures for study purposes. And essentially, they've pressed the end of the wood together, and that's where it broke at. Now, on an aircraft, you could get the same type of thing, and obviously you're going to be looking for those types of things. However, you can get these in lumber or in pieces of wood that you're going to go put on an airplane because of something that happened during the tree's life. Maybe there was a compression failure internally. You didn't see it, but then whenever you start to go through the wood, there it is. So you always want to have an eye out for that because that could also cause a problem whenever you go to install it on the aircraft. Okay, similar to the compression rings that you'll get inside of a tree, you could also get tension. They look very similar. So essentially, as the tree bows over because of the load that's on it, like you see in the graphic here, that the wood on the top has to grow really fast to basically to continue to to support the tree, and that causes those rings to spread apart. That tension failure is not acceptable for any aircraft or any wood that's going to be used on an aircraft. It's typically harder and denser, and maybe darker in color than normal wood, but is a serious defect, having higher than usual longitudinal shrinkage and may break down due to the uneven shrinkage. When in doubt, just reject it. Just the same idea. Like you'll have compression on one side, tension on the other. Typically, you generally just don't use them. It may be very strong and pass a hardness test, but just as a good rule of thumb to kind of work to that super high standard that you have to do with wood, just stay away from them. Okay, last defect we're going to talk about is just decay. We've already talked a lot about decay, and whenever we're inspecting an aircraft, it goes without saying that we don't want to put decaying wood onto an aircraft. So this is the last defect. Don't put decaying wood on an airplane. Okay, so let's talk about repairing wood structures. Like one of the first things that you could be asked to do is to reglue some sort of joint. So there's 5 principles when it comes to gluing wood together. First off, make sure there's a proper and equal moisture content of the wood to be joined together. So make sure that they're not overly wet, not overly dry, and the two pieces of wood are about the same. If not, the glue won't set right. Second thing is properly prepared wood surfaces that are machined or planed, not sanded or sawed. So don't sand it, because that will take a lot of the rough edges off the wood, and you need those rough edges for the glue for the glue to get down in there to create a really good bond to it. So you don't want to sand it down. You just want to plane it. You don't want to saw it either, because that has its own set of problems. That number three is a selection of the proper adhesive for the intended task, which is properly prepared and of good quality. So right tool, right job, just like anything else, but especially with wood or with wood glue that you're putting on there. Three or four, the application of good gluing techniques, including fitment, recommended assembly times, and adequate and equal pressure applied to the joint. That's what this graphic here is showing. That you don't just put some glue on it and stick it back together and then leave it like you would super gluing some part at your house or whatever. This, you need to put the glue in there and then put it under pressure and hold it together, so that way the wood and the glue have a good penetration, and they eventually form one cohesive unit. And we only can really accomplish that via pressure. So this shows pressure blocks and how to apply them. Fifth, performing the gluing operation under the recommended temperature conditions. Now keep in mind, just like this is like paint or any other type of chemical, that temperature has a massive effect on it. So don't glue whenever it's too cold. Don't glue whenever it's too hot. And then if you are going to do that, look at the engineering data for the glue and try to make your best determination of when that glue is going to be fully set up, and then give it a little bit more time on top of that before you do anything else with it. All right, let's say if you were to have a rib that gets cracked or damaged or whatever, your first option would be to simply just replace the rib, go and fabricate a new rib out of new wood, and then put it back in there. But let's say it's not that bad and you think you can just fix it. How do you do that? You can repair a cap strip of wood rib using a scarf splice, like the one that you see here. The repair is reinforced on the side opposite of the wing, covering the spruce block that extends beyond the scarf joint, not less than 3 times the thickness of the strips being repaired. Reinforce the entire splice, including the spruce reinforcing block on each side, with the plywood side plate. And you can kind of see the side plate right there. The scarf length bevel is 10 times of the dimension A that's on there, with the spruce reinforcement block being 16 times dimension A. The plywood splice plates should be the same material and thickness as the original plates used to fabricate the rib. The spruce block should not have a 5-to-1 bevel on each end. And so essentially what they're saying there is that you would be able to reinforce that rib by the application of those two side plates. Now, once again, this is not necessarily the best way to go about doing it. The best thing to do with a rib is just simply take it out, replace it, put a new one. But if you can't, this is a way how to do it, which is also captured in AC 43 along with the rest of the different types of repairs that you can do. Now, that being said, any repair that you do, AC 43 is just a basis for approved data. You could say, hey, look, I plan on doing a scarf splice per this type of repair in AC 43. You send it off to FAA and they say, okay, yeah, that's an approved repair. You can do it like that. But you can't just haul off and do it and then sign it off and return the aircraft to service. Okay, this is what the same type of repair looks like, but it's where multiple members come together at one point. You notice that it's a little bit more complicated, and you need to make sure that the grain of the wood is going correctly. But essentially, it's just another splice plate that's being put up against it that you'll then glue or attach as per your approved data that you're working to. But yeah, so that's what it looks like whenever cross members are involved. Same idea, it's just over all of them. Okay, same type of repair, just now a spar has been involved. So you notice that you've got the cap strip that goes on there. It's going to overlay all of those different members, and it does the same thing. The only difference is that like you have a joining piece of that cap that goes over the spar, and that what that's helping to do is transfer the load, or the strength rather, of the spar onto the repair. Okay, so what do you do if the spar itself is broken or damaged? Well, you can actually splice a spar just like you could splice any other piece of wood at any point, except for, and this is the one exception, you can splice them at any point except for where the wings join the airplane. So at or at the landing gear fittings, engine mount fittings, or the lift and interplane strut fittings. Like those are the places that you cannot splice a spar. But if it's just like a regular spar that's just run down the wing or down the fuselage or whatever, you can splice there. And you do it by the splice that you're looking at right now. You simply cut them off at an angle at a 5-to-1 slope, and then put them together. Now, the depending on what's going on, the slope can vary, but the it shouldn't be any steeper than 15-to-1. All right. Now this repair is actually in AC 43, specifically the tapered faceplate that you see here. Now, the chief concern with the tapering of a faceplate on a spar like this is going to be shrinkage over time and then the repair coming undone. So, there's a couple of suggestions for minimizing the effects of shrinking. First off, is use bushings that are slightly short so that when the wood member shrinks, the bushings don't protrude and the fittings may be tightened firmly against the member. Secondly, gradually drop off the plywood faceplates by feathering that you see here. So, like, don't make them all of a sudden come, to a sudden halt, but feather them out nice and evenly, and then thoroughly seal all wood surfaces, particularly the end grain and bolt holes, with a varnish, epoxy, or other acceptable sealer to slow or prevent moisture changes in the member. That will help slowing things down. And then if you have any questions on any kind of wood work like that, is you can always go to AC 43 and find it. Last thing we'll talk about is bolt holes. So bolt holes will get elongated, and you'll find this out with a composite tube. One of the best ways to fix those is actually fill them and then re-drill them in wood. Is just fill them with an epoxy or whatever, and then go through there. But however, whatever repair that you go to do has to be approved, and you can use AC 43 as a basis for repair, but what you can't do is just go all willy nilly. And especially with something like wood, you want to make sure that you're doing things correctly, and there's safety rails been put in place to prevent you from making a mistake, and that is that approved data from the FAA, especially on something that is kind of as unique as wood. So make sure that you always work to whatever data has been approved by the administrator, and as long as you follow the directions, you'll be good to go.